Hi, and welcome to Physics 401A, the course of Classical Mechanics 1. In the very first lecture, we will recapitulate some interesting and basic aspects of Newtonian mechanics which you have already learned. Even before doing that, let us understand what classical mechanics is. So, classical mechanics is a branch of physics which is dedicated to the study of the motion of physical objects, starting from point-like objects to objects of different type of size and shapes. Okay. If a body does not move as a whole under some circumstances, but it gets deformed. Okay, let's say we push or give some thrust to a body, like non-rigid body, like a dough of flour, and it gets deformed partially. So it really corresponds to a local movement of the system, and this is also belonging to the class of mechanics. Okay. Now, if a body does not move at all, even it does not deform macroscopically, but it responds to the external agent of deformation. Let's say if we just push, or we just give a like a thrust or something, give a blow of hammer, for example, to a brick, and the brick doesn't break, doesn't move, doesn't get deformed, but you can see, you can hear some sound, or you can see the recoil of the hammer. So this type, and you also feel like as a blower of the hammer, you will also feel some reaction. So this is also another kind of mechanics. Okay, in this case, where you have partial or let's say the total movement, we mostly say it's a case of dynamics, and where the body does not move globally, but it responds to the external agent by reaction force, or in other ways like producing sound or something. Then we can also say this is mechanics, and this is the class of subclass of mechanics which is called statics. Now this case is the case for rigid bodies, this one, and this is for the non-rigid bodies. Okay. Now, of course, if you have a non-rigid body or rigid body, under certain condition, I mean, depending on where you are moving, where you are giving the force, or how much force you are giving, you can always have the movement. Okay, so this type of thing you all know, like you can just easily, I mean, you can put a wheel on a under a brick or something, or you can make the floor very slippery. So, and then if you just push or something, then the body will move much more easily. Okay. So all these things, so the basic message is whether it moves globally or partially, or it doesn't move, does matter. The thing is that whether it tries to move even even microscopically, then we call it as a mechanics. Okay. A formal approach to such study of motion basically is in general done in terms of so-called dynamical theory. So dynamical theory is a general term used to study the time evolution of a system in any aspect. So here we will talk about the motion of a body. So with time the body changes its position, its velocity. So we can then talk of a reasonable dynamical theory. Now, for like other dynamical theories, the classical mechanics, which is the dynamical theory of the movement of physical objects, also needs two things. One is the state, and the state of the system. This means that is a situation, is the conditions, the instantaneous condition of the body, depending on the aspect on which the body is studied. For this case, this is the motion or the movement of the body. Okay, so the state of the system will be well defined at every instant of time. That's very crucial. Then, of course, there will be a law of evolution. Okay, you can also underline the state as well. Yeah, the law of evolution, that will give you the law or the rule according to which with time it changes its states. Okay. So you understand maybe intuitively what this is. And like classical mechanics, maybe you can also think of classical electrodynamics, which is consisting of four popular equations of Maxwell, and quantum mechanics, which is where the equation of dynamics is the Schrödinger's equation. So both of them are dynamical theories. Okay. Now you can, of course, I mean, I have already asked you a question over here, but I can ask you now that you can also think that what are the states and the evolution equation for classical electrodynamics and quantum mechanics, whereas we know for Newtonian mechanics, state is quite simple to understand. That is denoted by the position and the velocity at a given time. Now let's say we are studying the motion of particles, okay, or rather one single particle. Then at a given instant, time instant t, we would like to know where the particle is situated, and that is its position. Now if we just denote the position and not the velocity, then basically no information of movement is given. We don't know whether the system is moving or not with time. Then we give some velocity, and of course you know that if the velocity is non-zero, then there is a possibility of motion. Of course, if the velocity, instantaneous velocity is zero, there is a possible of motion. For that you have to know the time derivative of velocity itself. That is also true. And Newton's law basically is coming into that picture, that R and V sometimes is, I mean, the combination of R and V sometimes is giving a state, but it is still not sufficient to understand whether the system is really moving or not. And then, of course, or even if it moves, how it moves, then evolution equation comes, and that is your Newton's second law of motion, which simply relates this first time derivative, first order time derivative of V, or the second order time derivative of position, to the force. That is very crucial for classical mechanics. That is, the dynamics, or the dynamics means roughly the story of the story of force. So the dynamics is complete at the second order derivation of position, or the first order derivation of V. Okay. So this is what classical mechanics is, and that basically renders it to be a reasonable dynamical theory. Now we can do some recapitulation of the Newtonian mechanics as well, and where we will talk about three basic principles of conservation. The first one is coming from Newton's second law, which simply says that the time derivative of time rate of change of momentum, whatever the p is, the linear momentum, is equal to mv for non-relativistic case for a particle of mass m, is proportional to the external force. And what is external force? It is something which tries to change the inertia of the particle, right? That you all know, that is Newton's first law. Okay. Now it simply says that finally ddt of mv is equal to some k, constant of proportionality, times f external, and finally for a system of fixed mass, you simply have m dv dt is equal to k f external. And then by choosing a suitable unit of force, you can finally say that k is equal to 1, and your m dv dt is simply equal to f external. This is the popular form of Newton's second law. Now here you see that if external is 0, then you can say that the total mv is conserved. And this is the principle of conservation of linear momentum. Okay. Now in our course, unless stated otherwise, v dot will be denoting ddt of v, but not del del t. Del del t is the time, partial time derivative. Ddt is the total time derivative. I hope all of you understand the difference between the two. And then mv dot you can write is equal to f external, and then dv, if v dot is dv dt, which is dv dr dot dr dt. Don't get surprised by this division by vector or something. This is just a way of writing the dot product because it will be written in components, so you all understand what this is. So this is simply nothing but mv dot dv dr. This will be again simplified if I just write in this way, so that then you will be less surprised that mv dot dv is equal to f dot dr, right? and this is nothing but the infinitesimal mechanical work done, which is dW, you can always say. Then if you integrate between two states Vi and from initial velocity state Vi to Vf, and you say the total work done is W, then this is nothing but the change in the kinetic energy of the system, which is the famous work energy theorem. Of course, if Vf is greater than Vi, W or work is greater than 0, and if Vf is less than Vi, W is less than 0, right? This is of course depends on how you define work. So if you define, for example, your work like minus of F dot dr, for example, it's a convention, then it is exactly the opposite what you get, right? So this is the statement what I just said for work energy theorem, and this is another way of stating the conservation of total mechanical energy. Now for the special case, so we haven't assumed any special form for the force here. Now if we just consider the case of a conservative force field, which is irrotational in nature, so the curl is 0, so the force field always can be written as a gradient of potential function. Again, by convention we write minus of gradient V. Then you can simply write mv dot dv is equal to minus gradient of v dot dr, which is nothing but the total differential of this scalar function minus dv, and then you can simply say the total differential of this quantity is 0, half mv square plus v. So half mv square plus v is a constant of motion, and half mv square is the kinetic energy, v is the potential energy, you all know that. So this is nothing but our very well known conservation of total mechanical energy. Now what happens if we talk about angular momentum and torque, so which is some relation to the rotations, right? So angular momentum is nothing but the vector product of the position vector to the linear momentum vector, and then the torque is the total time derivative of it, which can be written like this. And as you know that V cross P vanishes because P is always m times V for non-relativistic case here. Okay, then it is simply, the torque is simply the cross product or the vector product of the position vector to the force. Okay, if this cross product vanishes, then the torque vanishes as well. And if torque vanishes, we say that L is conserved. That is very simple, you can understand. So this is nothing but the principle of conservation of angular momentum. Look, principle of conservation of angular momentum and linear momentum, they are the conservation of two vectors, so every component will be conserved. And the principle of conservation of mechanical energy is the conservation of a scalar, so there will be only one scalar which is conserved. Okay, so there is an example of such type of force where r cross F vanishes. This is known as the central force, where F is always directed along r cap, and that's why your r cross F is 0 and L is conserved. Okay, later we will of course revisit all these three conservation principles from a different perspective, that is the perspective of symmetry. Okay, here I end this subpart of the first lecture. In the next subpart of the first lecture, I will talk about the system of particles and the corresponding conservation principles. Thank you.